Aniruddhan, and this is my video demonstration for the project Automating RF Circuit Synthesis, specifically for the Resistive Feedback LNA. The specifications are given at 1.58 GHz and they are as follows. The single-ended gain needs to be greater than 10 dB, the noise figure needs to be less than 4 dB, the S11 needs to be less than minus 10 dB, the IIP3 needs to be greater than minus 15 dBm, and the power needs to be minimized. So moving forward, the first step as always is to build the schematic in Cadence, and that is what I have done here. This is the NMOS and this is the PMOS. The biasing has been done using a current mirror, and this is the resistive feedback LNA. I have added certain biasing details such as these inductors to input match the given network 250 ohm, and the initial DC operating point is picked such that the input impedance looking in from the input port is 50 ohm. That is the starting point, and these AC coupling capacitors are added to not change the small signal picture. Now I'll briefly walk you through the code. Again, the grossly important details of the code are in the definition of the loss function. The specifications have been very clearly defined here. The loss or the activation function used here is again a rectified linear unit, and the loss function is simply a sum of various other losses such as the gain loss, the S11 loss, the IDD loss, the noise figure loss, and the IIP3 loss. This is the linear combination of all the losses, and the gradient specific to this netlist is defined like this. And by needs edit, here I mean that depending on the specific topology, the gradient and the update function needs to be updated, otherwise the code is as generic as it can be. Moving forward, this function prints out the DC operating point. This function prints out the S parameters. This function prints out the noise figure. These functions calculate the IIP3. This function prints out the AC gain, and this function performs the main optimization. This function performs the sensitivity analysis. This function performs the temperature sensitivity analysis. This function performs the temperature analysis. Temperature analysis, as in the previous case, has been done at 4 different temperatures: minus 40 degrees, 0 degrees, 27 degrees, and 100 degrees centigrade. The process analysis is performed by this function, and the supply voltage variations analysis is done by this function. And this is the main function that integrates all the above functions. And as you can see, this code is being run for 5 times. This is done to reduce the length of the video and the space it occupies. In the previous video on the noise cancelling LNA, I had run it for 10 times to just give a very clear idea of how the code runs. Here I will run it only for 5 times since the idea remains the same. And I'll just describe the netlist also. So these parameters have been chosen based on the initial operating point described earlier. And this netlist is specific to DC analysis, AC analysis, S parameter analysis, and noise analysis. This netlist specifically performs HB analysis. That's why there have been 2 netlists defined. It's exactly the same as the previous case, only the command for HB analysis is added here. And now let's run straight into the code. Unlike the previous case where the best 3 netlists were picked based on the loss and the sensitivity and PVT variations were performed, in this case I will pick only the best 2 netlists and run the PVT variations and temperature analysis. So the first DC operating point has been picked. So this is just the operating point that has been predefined by the user. As you can see, it does not meet the specification of AC gain and noise figure. The IIP3 spec is also not met. Oh, sorry, it is met. As you can see, between the first and the second iteration, the AC gain has increased, the noise figure has gone down, the IIP3 has slightly reduced, but still is within our acceptable range. So it is good for us. As you can see, the power dissipated is continuously going down, the loss is going down. This is the first significant iteration, and the next case again the loss has gone down significantly. The AC gain has successfully met our spec. Now the IIP3 is still also within spec, S11 is also within our spec, and this is the fourth netlist. And as you can see, the noise figure is now clearly within our spec, and the loss is extremely small, 0.001164. And now this is the fifth time. As you can see, the loss function clearly goes down. Here in this case the gradient is much larger than in the previous case of the noise cancelling LNA. So now quickly we'll move on to the process variations and the sensitivity analysis. Since we have picked our two best netlists and we would run PVT and sensitivity on those two, this will take a slight amount of time. Now the temperature analysis is being performed on this netlist. As you can see, the two best netlists have been saved here, netlist 0 and netlist 1. These two are just the HB versions of the same. The temperature analysis is being performed. The loss at minus 40 degrees centigrade is printed. As you can see, the temperature analysis is complete, and the sanity check of this loss function being equal to this at 27 degrees centigrade is met, which means our code is working fine. And as you can see in the top TT process, the loss is exactly the same as this, which again confirms that the code is working all fine. Now the process variations are being performed, as you can see. As you can see, the process variations is complete. Now we'll move on to power supply variations. As you can see, again the loss at 0.9 volt is exactly the same as top TT process, which confirms that the code is working fine. So the voltage supply variations have also been completed. Now we move on to the sensitivity analysis for this first netlist. As expected, the temperature sensitivity is positive because the temperature analysis says that the loss increases with temperature, and the sensitivity is also positive, as you can see. So the full-fledged analysis for the first netlist is complete. Now we move on to the temperature analysis of the second netlist. As you can see, the loss at minus 40 degree has been printed. As you can see, the loss at 27 degrees centigrade matches with the loss obtained here, which is 0.00105884, which is exactly the same here, which confirms that the code is working alright. Now the temperature analysis is successfully complete. We move on to the process analysis. as expected, the loss in top TT process is exactly the same as the loss at 27 degrees centigrade. Now the process variations have been successfully completed. We move on to the power supply variations. And as expected, the loss at 0.9 is exactly the same as top TT or at 27 degrees centigrade, which confirms that the code is working fine. Now the voltage variations have also been completed. Now the only thing left is the sensitivity analysis for this particular netlist. Now, as you can see, the sensitivity and temperature sensitivity have also been printed. The sensitivity of the second netlist appears much better than the sensitivity of the first netlist. So, and its loss is also much lesser. So we can confirm that this netlist performs better than the previous one, and we can pick this netlist to be the netlist we want to use. So this brings me to the end of this video. So that's it for this video. Thank you.